together simultaneously in the 20th century. Now, the issue was that relativity on this side and quantum mechanics on this side, the physics of the very large and the physics of the very small, were not very well united. In fact, they were not united at all. They did not agree on certain things, and it made life very difficult. So these people probably hated on these people, and these people kind of hated on these people. And the fragmentation that existed between general relativity and quantum mechanics was sort of considered maybe something we just deal with. For example, you might see some of the literature about Niels Bohr. These types of people who worked mostly and focused on quantum mechanics side of things were probably accepting that physics of the very small works at those scales. At the very small scales, you cannot do classical physics. You have to deal with quantum mechanics. You have to deal with uncertainties. You have to deal with the probabilistic nature of the physics versus at the physics of the very large, such as general relativity. Maybe they should accept that that works at those larger scales, but cannot include things like what we see in quantum mechanics, because there were a number of quantum properties of these particles. More and more particles were getting discovered, but also quantum properties of those particles were also getting discovered, and one of them was spin. Now, why I mention quantum properties is because whatever physics is going to explain, describe, or predict this property, after it's predicted it and it's seen in experiment and it's been verified experimentally, if you are, say, suggesting some other physics or some other theory or some alternative way of seeing things, then you should kind of be able to produce those same properties or similar properties or something that would explain what we see experimentally. So in other words, say these people, classical physics people or general relativity people, and later on the string theory people, let's say these people did not like some of the things about quantum mechanics and they wanted to come up with a new theory, and we can call that the grand unification theory candidate, right? Because ultimately these people were thinking, why don't we come up with a broader, more general theory, grand unification theory, which can subsume all of the physics that we know so far, including gravitation, electromagnetism, and quantum mechanics. And these people especially did not really like some of the bizarre properties of quantum mechanics. But let's say the GUT people were working on the grand unified theory, but if they could not explain some of the things that were already seen in quantum mechanics, like fermions and how fermions were different from bosons, and that fermions had a different quantum spin than bosons did, spin being one of the properties of quantum mechanics, then that would be really bad. And actually, this is a sort of struggles that the grand unified theory people did face and did have to address in their work. And until you kind of include everything and explain everything that's already known, you wouldn't want to go backwards, right? In your quest to explain everything, if you then explain less things than what's known already, then that is not really good. And people would be very mad. And especially those people who have contributed to quantum mechanics and particle physics. I mean, they should not feel left out or feel like their work is a joke and now people are just throwing it out. And they cannot throw it out because these were experimentally found. If things are a result of experiment, if things are outcomes are coming out of doing experiments in the lab and they're real and you show the measurements, then you cannot deny them. Whereas there's a bunch of things that are theories which you can kind of deny until you prove them experimentally. So anyways, that's sort of the background in the early 20th century. And remember that people, especially the theoretical physicists, were looking for a grand unified theory. And string theory is a candidate for grand unified theory. It's considered maybe the only real game in town as far as a grand unified theory goes. So even though it wasn't until like 1960s, 1970s when string theory is getting properly developed, actually it was as early as 1919 when Kaluza and Klein took Einstein's general relativity and kind of extended it to add one more spatial dimension. And they were kind of modest Because as you know, string theory has 9 spatial dimensions, with 6 being the extra ones on top of the 3 spatial dimensions that we know and love and are familiar with.